So what's up, everybody? How are y'all? Doing good. Ready for the exam Friday/Saturday/Sunday, whenever y'all want to take it? Not quite? Well, hopefully we can get you over the finish line here soon, but today we're going to finish up section 3.8 and get into a little bit of chapter 4. The exam won't touch anything in chapter 4, so just know that in advance. Like the second we're through this section, this is the last of it. We've already talked a little bit about section 3.8. It's all about differentials, what they represent and how they can be interpreted. We said, in general, the differential of y, dy, can be represented as f prime of x times dx. But what does this dy dx mean? Because they're one thing. Dy is one thing, dx is one thing. And what they mean is incremental infinitesimal changes. So one way to think of dx, for example, is that it is the limit of the small change in x. So this is one way we can think of it. And having said that, if that's the case, then for really small dx's, delta x's, then we can think of it kind of like this. I'm trying to come up with the most concise way of writing this. Okay, do this. So for really, really small changes in x, all of these things are approximately equal to each other. Having said that, generally said, delta x is always larger than dx. Delta y is going to be smaller than dy. It's going to be bigger than dy. So generally, if you ever see something like the delta is always bigger. Make sense? Now, having said that, this isn't exactly clear just yet, is it? So why don't we unpack this a little bit? Let's look at what delta y is. Delta y, we know, is equal to f at x minus or plus delta x minus f at x, right? So if we divide both sides by delta x here, we're going to get delta y over delta x is equal to the difference quotient. So for really small x values, we're saying this thing is super similar to delta or to our derivative. Which makes sense, right? Because what's the derivative? The derivative is the limit as this delta x goes to 0, right? So as it gets really small, we start getting closer and closer to looking like our derivative. And in that way, we can think, like I said, of these differentials, dx and dy, as being approximations. Does this make sense? But since they're approximations, we can also think of them as error terms. That's another way of using them. We saw that in the last class. Yeah, let's check out some more. We've already gone through some of these. I think we already went over this example, didn't we? We talked about this one. So we want to find dy when x is equal to 1 and dx is equal to 0.01. Well, we know that dy and f prime of x are related to each other, right? You know, they're exactly equal. And we know that f in our case was equal to x squared. So the derivative of f is 2x. So to find dy, we're going to take and evaluate our derivative at 1. We're going to approximate dx as being the change of about 0.1 or 0.01, we need to say. So dy is going to be equal to function evaluated at 1 times dx, or 2 times 0.01, which is going to come out to be 0.02, right? Now, to compare this to delta y, well, delta y is equal to that change in x, right? Delta y now is the next thing we want to find. It's equal to our function evaluated at x plus delta x minus our function evaluated at x. In comparing these solutions, dy is 0.02, and the actual change in y, well, it's 0.0201. I was trying to get that decimal right in my head. So what we're saying here is that for small changes in x, dy and delta y are decent approximations for one another. Now, mathematicians have particular language about what we consider to be small, but generally, you can think of it as a number, a decimal value less than 1, greater than 0, generally. Having said that, An application of it would be marginal analysis, where we look at small changes in revenue compared to the demand, the units of the number of products sold. So we're going to say that delta R is approximately equal to dr. So notice then, dr dx, that's marginal revenue, right? So if we're going to approximate dx being something small, we've already found our marginal return, our marginal revenue, and we can approximate what the change in revenue is going to be. So having said that, we've got a demand function. We're going to set the price of an object, of a product, equal to 400 minus the amount of demand that it receives, the number of things that are sold, right? If that's the case, then revenue is going to be X times that, right? This is our profit function or our demand function. So our revenue function is going to be 400 x minus x squared. We're going to say that dx is going to be about 1. We're going to approximate it with 1 because the sales are going to increase from 149 units to 150 units, right? Which means then that X is going to be set at 149 because 149 plus 1 gets us to that 150, right? So we're going to start at 149. That's where our X value is. Now we're going to take the derivative of our function. So this is going to come out to be 400 minus 2x. So 400 minus 249 times 2, that's going to come out to be 398, right? 398. $398 minus the 400 minus the 398, so it'll be 2. Agreed? Wait, I did that wrong. 298. 298 minus 400 will be 102. My apologies. So now, dr is going to be equal to dr dx times dx, right? Well, dx is equal to 1, or approximated as being 1. So the change is going to be about 102. The change in our revenue will be. So looking at the math then, going through, we have dr dx that we found to be 400 minus 2x, same as ours. We're setting x equal to 149 and delta x equal to 1. And then we're saying, all right, let's go ahead and calculate all of this. Throw in 149, multiply by that delta x, and out comes 102. Comparing it then to calculating delta R the long way, where you have to plug in 115, you have to plug in 149, you find that it comes out to be 101. It's a pretty close evaluation, right? And these values come out to be pretty close together. So having said that, as another example, we have another function, this time for profit. It's a function of x represented as, for those of y'all at home who can't see this is slide 11 on week 8. But this profit function is going to be 0.0002x cubed plus 10x. X. What we're going to want to find is the differential dp when x changes from 50 to 51. So x is going to be equal to 50. Delta x is going to be equal to 1. The derivative of our function going to come out to be 0.0006 x squared plus 10. Now we're going to plug in 50. Evaluate this thing at 50 and multiply by 1. It comes out to be about 1150. Comparing that then to the change in profit, well, they only differ by 3 cents. So the point here is to say that this marginal analysis is a slightly quicker way of finding what the change in a thing is going to be. If you know the function of the thing, like we did, probably going to want to know the derivative at some point. So go ahead and grab it. And then plug in what values you're looking to solve for, right? To calculate about. Does this make sense? Having said that, differentials are not created equally. There's a couple different formulas that we're going to want to see. What I've got right now is the product rule up, but here are the rules of your differentials. Notice they do change a lot, right? But generally what you got is wherever you see, how do I want to say this? I don't know how I want to say this. Let me go back to the product rule. Back in the product rule, if we had u times v, and took the derivative of that, we would have u times dv dx plus v du dx, right? But then we're going to multiply all the way through by the differential dx and end up with u dv plus v du. So wherever you see a derivative with respect to x, that's going to reduce in some way, most likely. Makes sense? So as a couple examples of different differentials, we've already seen x squared, but looking at something like 3x plus 2 over 5, the differential will come out to be dy is equal to 3 over 5 dx. Something like 2x squared minus 3x come out to be dy times, or dy is equal to the quantity 4x minus 3 times dx, so forth and so on. So this is that problem I was talking about last class a little bit. As one, or this is moving into that problem rather, talking about one possible interpretation for these differentials is error. In this problem, we're going to have a ball bearing that's measured to be 0.7 inches. So with that said, the volume of the ball bearing should come out to be about 1.4368 cubic inches. But we know that there's error associated with our measurement. It's going to be off by about 0.01 inches. Having said that, we want to know how far off the volume could be. Never mind the fact that we already truncated a bunch of numbers off because we're multiplying by pi. We want to know approximately how far this is going to be wrong to. So having said that, we know v as a function of r is equal to, like it says, 4 over 3 pi r cubed, right? So dv dr is going to be 4 pi r squared. This is of course v prime, right? So we know r is measured at 0.7 or 0.7. And the possible error in that measurement is up to 0.01 inches. So dv is going to be 4 times pi 0.7 squared times 0.01. Now, I'm not going to pretend to know what that number is. So I'm going to skip to the solution here. What we've come up with is that the error can be up to 0.0616 cubic inches. Oh, 0.0616 inches cubic. Now let's go back to what we found the volume to be initially. Initially, we calculated the volume to be 1.4368. But we have error in the second term, right? So we can only trust our result up to the first decimal. Make sense? And even then, some people would cast shade on that. Like, well, it's high enough, it could add over and knock your first decimal off too. Okay, sure. But this ultimately is just saying trust the first two digits here. Having said that, we could also do something like calculate the percent error. And their points here at the very end is just, let me step back for a second. Notice when I calculated this dB, I didn't have the plus or minus here. That's because it's understood that this is error, and error is above or below, right? So when you calculate it out, you don't necessarily have to have that plus minus there. But when you start using it, you do. Which is why they have the plus minus here. To let you know in advance, you're going to have error above and below. Now what they've done from there, they said, all right, now what we've got, what we measured it to be was 1.4368. Subtracting the error and adding the error, this is the range we can expect our volume to sit within. So about 0.12 cubic inches, not very big actually. Makes sense? People at home, what do y'all think of this?
It's a lot, but we got it.
Awesome. Sweet. Now, something else that we'll sometimes talk about is what's called relative error. Relative error is your percent error. It's if you measured this thing to have a volume of whatever, that error measurement divided by the volume gives you a percent error. So what we're saying is, compared to the volume that we measured this sphere to have, you can add or subtract this particular percentage of that volume to get the actual volume. Does that make sense? So this is the measured volume. And what we're finding now with the relative error is what the measured volume is compared to what the actual volume could be. So I don't have a decent meter stick, but I do have some standard sized things. All right, so the point of this is to say, you have an assembly line producing off chalkboard erasers. Chalkboard erasers are supposed to have a particular size, right? But they're not always going to have that exact size. What this is recording is the deviation from the actual size to the measured size, or vice versa, I should say, from the measured size to the actual size of one of these erasers. Does that make sense? Kind of, sort of. Percent error, I think, is always easier to understand after you've used it. Having said that, let's get into section 4.1. 4.1 is all about exponential functions. An exponential function is any positive non-zero number raised to an x value. Anything in this form. Now notice, we didn't say what x can be or can't be, right? It's because x can be whatever we want it to be. As long as it's in this form and a is larger than 0, it's an exponential function. Now, some properties of exponents. A raised to the 0th power is going to come out to be 1. The product is going to come out to be the addition of the exponents, as long as the bases are shared, right? So if this was A and this was B, we wouldn't be able to apply this property. But because they share the same base, we can. Similarly, division, we have the exponential function raised to another exponent. That comes out to be the product of the exponents. So forth and so on. As a couple quick examples, let's look at A, F, and D really quick. A up here is 2 to the second times 2 to the third. Well, we could go ahead and evaluate this to be 4 times 8, right? Which would come out to be 32. Or we could use our rules of exponents and say, well, this is 2 to the 2 plus third power, 2 to the 6th, 32. Two to the 5th, my bad. Bad math. Just looking at it like that's not 2 to the 6th, Matt, but I know I did everything else right. Now looking at D, we've got 1 to the third, or 1 over 3 raised to the negative second power. This is going to come out to be 1 raised to the negative second over 3 raised to the negative second. This is going to stay 1. This is going to become 1 over 9, or just 9, right? In other words, another way we could have done this, we could have applied the negative power first and treated it like in which case then we would have had 3 to the second or 9. So we can mix and match the order these rules are applied in. And finally, looking at F, the bases aren't the same, so we really can't do anything here other than simplify it. And to show you what I mean, this is going to come out to be 2 times 3 to the 1/2 power, or 6 to the 1/2 power. Everybody cool with this? Looking at these really quick, 32, 9, and 6 to the 1/2. So I have not led y'all astray yet. Now notice they're not showing that you can apply multiple ordering of these different rules, which is why I wanted to do this way really quick. Just to point out that you don't have to follow these rules exactly step by step. You can apply them in different orders if they present themselves, like with B. All right, so having said that, common question in all of these classes, when the hell am I going to use this stuff? Well, unless you're a biology student, you might not use it for carbon dating, but one application is carbon dating. So what carbon dating is you look at the ratio of isotopes of carbon-12, I think it is, compared to carbon-14. And sometimes they'll use other different isotopes of other compounds and chemicals. But they use that to set up an idea of how much or of how old particular items are. In the case of organic material, they use carbon generally because we know organic material, as long as it's alive, is going to have a certain ratio of carbon-14 to carbon-12. And this is how we're able to use it to calculate the age of a thing. And in this question, what they're asking is, given that the ratio is equal to 1 to the, or my mistake, 1 over 10 to the 12 times 1 over 2 to the t divided by 5,715. So let me write this on the board. Given this, we want to find out what the ratio is going to be for different years. So if something's been deceased for 10,000 years, 20,000 years, 25,000 years. And all we're going to do here is plug in each of these years for t and calculate what 1/2 is raised to that power, right? So looking at all of this, plugging in 10,000, we get approximately 2.973 times 10 to the negative 13. So you have 12 decimals and then a 2. 8.842 times 10 to the negative 14. So 0.13 zeros and then an 8. And then 4.821 times 10 to the negative 14. So really all we're seeing here is how to actually do the arithmetic here. What they're trying to tell us with this problem is that in order to calculate r at, well, let's just say 5715, that'll be a nice easy number to work with. Take and plug it in and do everything the normal way we would. Mistake, I meant to say 5. So having said this, some notes and notation, because you're undoubtedly going to use your calculator for some of these problems. If you see E as some value, it's the same thing as 10 raised to that value. So I could have written 5 times 10 to the negative 13 as 5e negative 13. So just as a note on how your calculator might write some of these values. Having said that, this next example wants us to graph out a couple of these exponentials. I'm just going to go ahead and jump to what they look like. 2 raised to the x was kind of like a hockey puck, a hockey stick. As does 1/2 raised to the x, but it's reflected, right? And then 3 to the x also looks like a hockey stick. So generally said, these graphs are going to look one of 2 different ways. If A is between 0 and 1, it's going to decay. And if we think about it, it kind of makes sense, right? Let's take, for example, A to be equal to 1/2. At 0, this is going to come out to be 1. At 1, This is going to come out to be 1/2. At 2, this is going to come out to be 1/4. At 3, it's going to be 1/8. At 4, it's going to be 1/16, so forth and so on. And we can actually see that here. And if we move in the negative direction, it's going to grow. So we have what's called exponential decay here. Anytime A is between 0 and 1, we have a graph that's going to look something like this. Now, on the flip side, if A is greater than 1, we're going to have the reflection of that. So on the flip side, if A is greater than 1, we're going to have the exact opposite case, right? The reflected case. And notice in every exponential function, you're going to have the point 0, 1. And that's because, should I say in every exponential function? In every simple exponential function. And what I mean by that is A raised to the x. In every simple exponential function like this, you'll have the point 0, 1. And the reason why I want to make this point about it being simple is think about if we added 1 here. So it was A to the x plus 1, then it would shift this accordingly, right? So having said that, in the case where A is between 0 and 1, you have exponential decay. In the case where A is greater than 1, you have exponential growth. Just some notes about the general characteristics. Y'all are going to want to come back to this later on your own. This is on slide 30. In the meantime, let's out at 650, right? Okay. In the meantime, let's consider this function here, 3 to the negative x minus 1. Now, for those of us who remember how graphs transform, we can think of f of x as being equal to g of x plus 1. My mistake, minus 1. And we can think of g of x as 3 to the negative x, right? Now, g of x equal to 3 to the negative x. We can rewrite this as 1/3 to the x. And when we do, we see, hey, this must be an exponential decaying function, right? It's going to look something like this. Now, for those of us who remember anything about the transformation, the simple transformations of graphs of functions, we'll remember that if we have a function and add or subtract it, we're just going to move it up or down, right? So here, we're just shifting our function down by 1 unit, right? So that means f of x is going to look something like this. Now, of course, this isn't precise because I didn't go through and find points and graph it point by point by point, but we see generally the idea. Jumping to a more precise example of how to do this problem, or a slightly different example, I should say. The first thing they did is they went ahead and found a handful of points. They applied the limit as x goes to infinity and said, hey, this thing goes to 0, this thing stays at 1, so the limit must be -1. I left that out here. Then they said, we have a horizontal asymptote at -1. This thing's decaying. We know that at 0, this thing has to be 0 now. Now we can go ahead and graph it. And I did not copy that graph over, but the graph would be more or less the same. Having said that, concept check on slide 33. But jumping into section 4.2 now, we have a new definition, an irrational number called E. I want you all to look at this for a couple of seconds and soak it in. What do you think this thing is doing? Why do you think anybody would even look at this other than they were a sadist? What is this thing doing? Folks at home, what do y'all think? Does anybody try to graph this? Let's look at the graph. One plus x raised to the 1 divided by x. Okay, looks kind of like an exponential function that's decaying to some value, right? Kind of what it looks like. But we have the limit as x goes to 0. So E must be this value here, right? Now I point this out to y'all for a particular reason that'll hopefully, upon reflection, show itself, like make itself obvious to y'all later after the end of this chapter. But the reason why this particular function was being looked at, why this particular equation was something mathematicians even cared about, was it has something to do with the derivative. This particular setup has a very special derivative. Having said that, let's get into this section. So, 1 plus x raised to the 1 over x, as we take the limit, x going to 0, that's going to give us this value E. E raised to the x, it's just going to be another exponential function, right? It's going to look like this. Nothing too crazy here. All we're doing is we're taking e and raising it to the negative second, negative first, 0, 1 second, so forth, so on. We find, hey, this thing looks like a normal exponential, right? Exponential growth, so it decays as we approach negative infinity as opposed to positive infinity. Now let's back up for just a second here. We said that e is equal to the limit as x approaches 0 of 1 plus x raised to the 1 over x. And here, we're taking it and raising it to another power. I'm going to choose another variable other than x, just to make this point. We're raising it to the y power. So we can rewrite this whole thing as the limit as x goes to 0, 1 plus x, y over x is equal to e to the y. Now I point this out because when it comes to why this is special, this is where the trick starts coming in. Having said that, there are some other particular types of growth functions you all should be familiar with, in particular logistic growth function. This is perhaps one of the most important functions in the biologies. It shows up in ecology, all over the place. When you're measuring things like population growth, so things like population growth in a culture, things like population growth between birds, shows up all over the place. Having said that, this is the graph of a logistic curve. I thought this is a good question. Does this look familiar to y'all? Folks at home, looking at this logistic growth curve, does it look familiar to y'all?
Yes.
Yeah, what does it look like? Anything from recent history? How about now? Is it starting to look like anything you've seen recently? These data points are hospitalization data in relation to COVID. So modeling things like the growth or the spread of a disease through a population is modeled with a logistic curve. So as another example of why do we care? This is abstract ambient noise that happens in the background, blah. We care because these are the types of models, the types of equations that like hospitalization rates of COVID. So I thought it would be worthwhile to point this out to y'all. Having said that, this is such an important point. I thought y'all should see where it's derived from. Ordinary differential equation of this order, of this form, I should say. But don't expect y'all to solve it. It is tough to solve. It takes a little while. I just wanted y'all to see, get an idea of what some of this stuff comes from, what it looks like, and how it's used in reality. Mike's still on. I don't know who it is, but your mic's still on. As another example, or as an example of where this gets applied, we have a bacteria culture that's growing according to a logistic growth model. We've found what the particular model is. Now we want to know what the weight of the culture is going to be after some time. So all we're going to do here is plug in 0, 1, and 10 for t, calculate the exponential like we normally would, then calculate the fractions like we normally would. Nothing major here. Excuse me. So 1 gram, 1.07 gram, 1.24 gram. Like I said, nothing revelatory here. We're just doing arithmetic right now. Another example of where these sorts of exponential problems show up. Interest rates. I thought about using my student loans as an example for this, but it was way too depressing. I have $130,000 at a huge interest rate. I don't want to know what that's going to look like anytime soon. Thank you, 2008. But having said that, there's some details we should know about interest rates and the way things compound. If we say interest rates compounds annually, let me actually write this out on the board so it's more clear. Put it out of the way. Okay. That is equal to P1 plus R. You wrote it again the other way. R over N raised to the N. All right. So if in our equation or in our setup of our problem, we're told that our interest compounds annually. That means N is set to 1. If it's semi-annually, N is set to 2, quarterly, 4, monthly, 12, daily, 35. Now, having said that, I want y'all to check something out here. We can play with this a little bit and find that if we let N approach infinity, this thing approaches P times e to the R. Let me actually go through and show the derivation so that it'll be clear. All right, so we're going to set x equal to R over N. Okay? When we do that, we substitute that into this, we're going to get that A is equal to P times 1 plus X. Well, this isn't R over N, it's just N. But let's imagine that we rewrote this as N over R times R. Okay? Then now we have 1 over X here times R, right? So putting that together, this is going to come out to be 1 over X times R. Agreed? So having said that, now we're going to get that the amount is equal to 1 over X, that quantity times R. Well, hey, I could bracket this off, right? Apply the limit as X goes to infinity here. And notice what ends up happening now. Let me write it slightly different. P times one plus X raised to the 1 over X raised to the R. Okay. So if we send X to 0 here, is what I meant to say, not to infinity. We send X to 0, then what we're going to end up with is going to be P times E raised to the R. Now, why would we send it to 0? Why would we send X to 0 here? Because that's like sending N to infinity here, right? And if N goes to infinity, then what we're really saying is we are continuously compounding interest. So the formula for continuously compounding interest is going to be P times E raised to the R. Does this make sense to everybody? Kind of, sort of? Cool. Well, that is on, for those of y'all at home, slide 46. I would highly suggest everybody go check it out. Just to kind of reabsorb all of this and make sure it makes sense. So having said that, we have two different forms of, or two different interest formulas, I should say. We have the formula where it's compounded n times per year. That's that formula that we started off with. And then we have compounded continuously. It's going to be this one. More particularly, I should write it in terms of time. So the amount owed, T, is equal to the initial amount you started with, is 1 plus R over N times N with T. This is compounded n times a year. Oh, how can I not spell that today? And then compounded continuously. We have AT is equal to your initial amount times E raised to the RT. So what is all of this? What are these variables representing? A represents the amount due. T represents the time elapsed. P represents the initial amount. R represents the rate. So if this is a loan, the initial amount would be whatever the cost of the house, the car, the student loan, whatever it is, right? Times the rate times the time. Times E raised to the rate times the time. Make sense? So, in the 4 minutes that we have, let's consider this quick example. You deposit $12,000 into an account that, with the instructions that the account will be turned over to a nephew on his 25th birthday. So, in 25 years, we're going to compare the interest, the balances, based on four different criteria. The first criteria, you have 7% interest compounded continuously. The second is 7% interest compounded quarterly, and then 11% same conditions. So checking this out, in the rate that, or in the case where you start off with $12,000 and it compounds at 7% quarterly, continuously, then in the end, you have $69,000. Quarterly, you have 68. 11% compound continuously is 187. And then 11% compounded quarterly is 180. Moral of the story. Let's imagine this was a student loan situation. If you had a student loan of $12,000 and it compounded continuously at 7%, after 25 years, you would owe $69,000. If it compounded quarterly, after 25 years, you would owe $68,000. 7% actually is a pretty common student loan number. That's why I pointed it out. They range anywhere from like 375 to 12, I think, right? Isn't it like 12.5? Yeah. So, just as a heads up, when are you going to use it? You can use it right here, right now. Looking ahead, just for your own personal financial well-being, this is good to know. Please, please, please make note of this. Actually apply it. Because student loan debt is a horrible thing to be stuck with if you don't know anything about it. Anyhow, having said that, I will let you all out. If you have any questions, I'll stick around.